So hopefully everybody did super duper well on that. Since we had the answers still on the board for the quiz that was very, very similar to it, right? Okay, so now everybody is finding the paper called Precal A, period 5 is the best class in the world. It's about halfway through the packet. It's all typed. Alright? So here we go. Question number 1. How many ways can 1 man and 3 women be selected from a group of 10 men and 7 women? This is your homework. Please do it on a piece of paper. So we have 10 men and 7 women. How many ways can we get 1 man and 3 women? What do you think? What's that going to look like? 10C1 times 7C. What do you think, class? Is she right? I think she's exactly right. Do we care what order we're getting these people in? Is there any reason to believe the order matters? No. We just need to pick 1 out of the man pile and 3 out of the woman pile. Good job. All right, what's the probability of drawing exactly 3 aces if 6 cards are chosen? Now, first of all, this is a probability question, right? Trevor, what's on the iPad?
No.
1 perfect paper does not make you the Precal guy. This is a probability question, so what does that mean? Our answer is going to be a fraction. What's going to go in the denominator?
52C4, 52C2, 52C3.
Keep going, Robert.
52C5.
Almost.
6?
Why is it 52C6 this time?
Because that's what it tells you.
Because it tells you it is a 6-card hand. So your total number of 6-card hands in a regular deck is 52C6. Now, what do we want in the numerator? We still need 6 cards, right? But tell me about the 6 cards that go in the numerator. 3 of them are aces, and 3 of them are not. Okay, so here's your deck split into 2 piles. How many cards are in the ace pile? 4. And how many of those do you want? 3. So you're going to start with 4C3. Those are the aces. Now, how many cards are in the not ace pile? 48. And you want 3 of those? And that is the answer to the question. Does that make sense to everybody? What is the probability that in Kyle's family of 7 children, there will be at least 6 girls?
So on the bottom, would you put 7C6?
This is a little tricky.
2C1.
This is a different kind of probability. This is a binomial probability problem because every time Kyle's mother has a baby, the probability starts over again. You see what I mean? You know, she has a baby, okay, it's a boy or a girl, but then she has another baby, and it doesn't make any difference if the first one was a boy or a girl. This one's going to be a boy or a girl with still the same probability. That's a binomial probability situation. You're doing the same experiment over and over again, and the probabilities never change. Now, that's different than a card problem, kids. Card problems aren't done that way, because as soon as you pull 1 card out of the deck, what happens? The probabilities change, right? Unless you put it back. If you put it back, then it's okay. But you never make a hand if you kept putting it back. So with card hand problems, we have to do it as a combination situation. Because you're reaching in and you're not doing an experiment and then doing another experiment. You're grabbing 3 cards all at one time. This is a different scenario. This is, I'm gonna have 6 girls and 1 boy, or I'm going to have 7 girls, right? And every time I have a baby, it starts over. The problem starts over. So think about this for a minute. If you have 7 kids, okay, here's the 5th row of the triangle. I remember this because somebody wrote it down over there. Here's the 6th row of the triangle. And here's the 7th row of the triangle. Now, what do the numbers in the 7th row of the triangle represent? This is what? All of one or the other. So this could be all girls. What would this be? 6 girls and 1 boy. This would be 5 girls and 2 boys, and so on. Now, if you wanted to do combinations, if we want 6 girls, we could say 7C6. That's, I'm going to have 7 kids, and I'm picking 6 of them to be girls. That number is 7. That's 7. But if you want to do it this way, you absolutely can. But then you're done with the combinations, because then you have to put 1/2, 1/2, 6 and 1. Now what are those numbers?
Guys and girls.
That's the probability of a girl and the probability of a boy. And I want 6 girls and 1 boy. Now you can get that coefficient however you want. You can get it out of the triangle, or you can get it this way. What would this coefficient be? Well, it's 1, but it would be 7C7, because you're going to have 7 kids and all 7 of them are going to be girls. Here I had 7 kids and 6 of them would be girls. All right, so what's this piece look like? That's 1. 1/2 to the 7th, and I'll go ahead and put this down, but you don't really need that part. Got 7 girls and no boys. And then you'd get 2 answers here, and what are you going to do with them? Add them, because it's one or the other. Okay, now I know this is confusing, because depending on the problem, you handle it differently. You have to get a sense of when the problem's going to be set up like this. The problem's set up like that when you're doing an experiment, and we call it an experiment, rolling a die, flipping a coin, raining or not raining. When you're doing it over and over and over again, and the probabilities never change. That's when you do binomial probability. Okay? Jamie? All right. Next. Where am I? How many ways can a chairman and a vice chairman be chosen from a group of 8 students?
That's 8P2.
That's 8P2. You're exactly right. And why are you saying P? You're exactly right. Why are you saying P?
Order matters.
Order matters. We're not picking a committee. That would be 8C2. We're saying your chairman and your vice chairman, which is different than your chairman and your vice chairman, right? The order matters. Everybody got it? How many ways can 7 books be arranged on a shelf if 3 of the books are identical? Dan?
That'd be 7 factorial divided by 2 factorial.
It totally would be. Why is it 7 factorial?
Because there's 7 books.
Because there's 7 books. And one thing that you just have to know is, if there are 7 things, they can be arranged 7 factorial ways in a row. Now, in a circle, it would be 6 factorial, but in a row, it's 7 factorial. And a bookshelf, we're assuming, is a row. Now, why are we dividing by 3 factorial? Because the books are identical. And when we have identical things, we divide. How many ways can I select a committee of 3 to represent the 10 back row boys?
10C3.
10C3. Does everybody understand why that's a C? The last problem we did was a P, this one's a C. Order doesn't matter, we're picking a committee. Who cares? You just want to get picked, right? In my class of 39, 15 students like the like brownies. 6 will not eat either one. What is the probability that if I choose one student, he or she will like both brownies and banana bread? All right, stop and think. Of all the different things, the different ways we've approached problems, what might be a good way to handle this one? A Venn diagram. Because you've got two sets that overlap. So let's look at a Venn diagram here. And here is the class of 39. And I really did have 39. I had to move classrooms. I had to move to a different room. There were so many kids. They were wonderful, but there were a lot of them. Okay, so we had 39. And 6 of, okay, so we got brownies and banana bread. And 6 of them don't like either. So I'm going to put 6 kids out here. They are not part of the circles. Does that make sense to everybody? Okay, now wait a minute. 15 like banana. Okay, now wait. All right, so now the 6 kids who don't like anything are out of the mix. So now I'm down to 33 kids. Would you agree with that? Okay, so these 6 I've sent out to the hall. Now there's 33 kids left in the room. And I say, raise your hand if you like banana bread. And 15 hands go up. And I say, okay, put your hand down. Now raise your hand if you like brownies. And 28 hands go up. Now wait a minute, there's only 33 kids left in the room, right? How many hands went up? 43. Now wait a minute, what had to have happened then if 43 hands went up? Some kids raised their hands twice. How many raised their hands twice? 10. So there are 10 kids here in the middle. Because there were 33 kids in the room that all like something. Everybody in the room is going to raise his hand. 43 hands went up, but there's only 33 kids in the room, so 10 people raised their hands twice. Does that make sense to everybody? Now, how many kids like brownies?
18.
Just brownies would be 18 because the whole circle is 28. And how many like banana bread?
5.
Just 5, like only banana bread. Now, does that take care of the 33 kids? Is that 33 there? Yeah. So now we can answer whatever question is asked, which is, what is the probability that if I choose one student, he or she will like both brownies and banana bread? Okay, this is a probability question, so the answer is not 10. The answer is 10 over 39. Remember, there's 39 total kids in the class, right? So it would be 10 out of 39. Very good? Okay, what's the probability of getting at least half right on a 4-question multiple choice quiz if you randomly guess at each question? All right, now stop and think. Question 1, you're going to randomly guess. Pretend it's in Russian. You have no idea. You can't narrow it down. So you're going to guess at that one. All right, now you go on to question 2. Aren't you starting over?
Yeah.
And you're guessing again. This is going to be a problem that's done just like this one. Because every time you guess, what's going to happen? You're going to get it right or you're going to get it wrong. And the probability never changes. Right? Never changes. So we need to get at least half right. Okay, what does that mean?
You get 2 out of 4.
I can get 2 right, or I can get 3 right, or I can get 4 right. Would you agree with that? Now, if you want to use the triangle, that's great. You would be using the 4th row of the triangle. It's hard to build it up backwards. 1, 4, 6, 4, 1. All right, so here we go. 2 right. What does this number right here represent? That's 4 right, 3 right, 2 right. So you can either do 4C2, 4 questions, pick 2 of them to get right, or you can pull the 6 right out of the problem, out of the triangle. Now, each question has 3 options. If you are randomly guessing, what's your probability of getting it right then? 1/3. And you want to get 2 right and 2 wrong. Does that make sense to everybody? Now, what does 3 right look like? Well, your coefficient would be 4, or if you prefer 4C3, 4 questions, pick any 3 of them to get right. That's a 4. Probability still 1/3, 2/3. Is that okay with everybody? And then what's 4 right look like? Well, that's 1. Or 4C4, 4 questions, all 4 right. And that would be 1/3 to the 4th and 2/3 to the 0th, which you don't need to include that, but I will just for consistency. And what would I do with all of those answers? Add them up. All right, read question 9 and think about different things we've talked about in terms of strategies. What do you think might be a good strategy for number 9? Think meatloaf and peas. Make a tree diagram. I would. I think it's the easiest thing to do. Because the probabilities change in the problem, right? Depending on whatever. All right, so what happens first? Either we have lacrosse practice or we have no practice. And what's the probability that we have lacrosse? 65, so there's a 35% chance we don't. Now, what happens?
If he has practice.
He either does his homework or he doesn't do his homework, right?
Yeah.
All right, so here we go. If he has practice, there's a 10% chance he'll do his homework, which means there's a 90% chance he won't. If there is no practice, there's a 42% chance he'll do his homework, which means there's a 58% chance he won't.
Yep.
And the question says, find the probability that Adam will not do his homework. Okay, now wait a minute. He cannot do his homework here, or he could not do his homework here. Would you agree with me? Now, what do? This branch represents practice and no homework. So what am I going to do with these 2 numbers? I'm going to multiply them because these are both happening. He has practice and he does not do his homework. So these get multiplied. What is 0.65 times 0.9? Point what? 585? Is that what you said? Now, this branch represents no practice and no homework. So what am I going to do with these 2 numbers? Multiply them. What do I get there? 0.203. Now, he cannot do his homework and have practice, or he cannot do his homework and not have practice. We have this branch, or we have this branch. So I'm going to take these 2 numbers and add them. Whatever that is, yeah. Okay, 1 more, and then your homework's done. God bless you. Actually, God bless me. How many 5-card hands from a standard deck will have more red than black. Now, this is not a probability question, so it's not a fraction. It just says how many hands, 5 cards, will have more red than black. Okay, now what does that mean? More red than black. What scenarios do we have?
3 black.
We could have 3 red and 2 black. Or we could have 4 red and 1 black. Or we could have 5 red. Does that make sense to everybody?
Yeah.
Now we're picking cards out of a deck. We're making a card hand. What's our setup when we do card hands? Combinations. Okay, so what's this one look like? 26C3, that is your reds, times, because it's 3 red and 2 black, so we're timesing 26C2. I'm picking 3 out of the red pile and 2 out of the black pile. Or, what's this look like? 26C4 times 26C1. Or 26C5.
You add them all together.
Add them all together. Because it's 3 red, or 4 red, or 5 red. Okay, got it? All right, when we come back from break, kids, we'll do a little bit of review, and then we're ready to take a test over this. We've actually learned it all, so we'll be ready to do that. Okay? You quite comfortable, Emma?
I was, yeah.